Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So this week we're going to look at the chapter 1, Introduction and Review of Wireless Communication Fundamentals. So this is the basic equation that you need to remember and also understand. So in this equation we have C equal to F lambda, F times lambda. So C is the speed of light, where in vacuum or air it is close to 3 power of 8 milli per second. But however, the actual speed of light is this value over here. So in your calculation, you can still use this number or this number, is up to you. However, it's easier for you to use this number for the speed of light. So it's okay. And then usually this equation we're going to use it to find the lambda here. So lambda here is the wavelength, the total wavelength, where F is the frequency. So we know that the speed of light is constant. So the frequency, for example, if you're going to look at Wi-Fi, which is 2.4 gigahertz, so we know we can find the lambda using the equation over here. Why lambda is important? Because we're going to use this value, the wavelength, to design and also to mostly to design antenna, RF and microwave devices. So this value here, lambda, is important. So what if frequency is increased? So if a frequency increase, the lambda will decrease because it's C divided by F frequency. So F increase, lambda will decrease. So if you look at the antenna, for example, Yagi Uda antenna, or you call it fishbone antenna, the frequency is around 4 to 800 megahertz. So that's why the antenna is big, is large, because at low frequency the lambda is increased. So the antenna is depend on the value of this lambda. So the larger the lambda, the value of lambda, the larger the antenna. Okay. So this is an example for an antenna, a Yagi Uda antenna, or you can call it a fishbone antenna, but for the scientific name is we call it Yagi Uda antenna, because the pelopo or the designer for this antenna is Yagi and also Uda from Japan. Okay. So usually the most common frequency that the commercial or free band use is from 300 megahertz to 3 gigahertz. For example, for broadcasting, for television broadcasting, it uses frequency from 300 to 800 megahertz. For Wi-Fi, it uses 2.4 gigahertz, so it's basically in the UHF band, ultra high frequency band. This is another example antenna at 2.4 gigahertz. So usually you can see this type of antenna in your router or in your access point. So it uses a monopole antenna. So it's just a straight wire inside here to produce a frequency 2.4 gigahertz. And then this is at 6 gigahertz, is basically at the microwave band. So if you look at this, UHF is 300 megahertz to 3 gigahertz. So for microwave band, it starts from 3 gigahertz until 30 gigahertz. Okay, that is the microwave band. And upper than that, we call it millimeter wave band. So millimeter wave band start from 30 gigahertz until 300 gigahertz. Is we call it millimeter wave band. Okay. So let's look why most of these technology or wireless technology increases its frequency usage from 1980 to 2021. This is the current technology lah. So what you're looking at here is the evolution of the cellular communication from 1G to 5G. Okay, so 1G started at 1980 to 1990. So it uses analog signal frequency at 30 kilohertz, so it's really low, and the bandwidth is at 30 kilohertz only. So let's look at these three parameters lah. Okay, so you can see the comparison from 1G to 5G. What is the difference? And the data rate is only 2 kilobit per second. And then the evolution goes to the 2G from 1990 to 2000. So it uses frequency at 1.8 gigahertz, and then the speed or the data rate is 64 kilobit per second. So it's much faster than the 1G, which is around 30 times faster. And this start the digital communication. So in 1G it still use analog signal. So 2G is start with the digital, and then starting 2000 to 2010 it uses the frequency at 1.6 to 2.0 gigahertz, where the speed goes up to 2 megabit per second. So this started we call it internet lah. We can access the internet through the phone, where it utilize CDMA each technology lah. So at this time the speed of the internet is quite high. You can access Facebook and other apps in the 3G evolution. And then at 4G we goes to LTE and Wi-Fi, where the speed is, I would say, 500 times faster, where it can goes up to 1 gigabit per second. So the frequency uses is 2 to 8 gigahertz. So in Malaysia, for 4G we use at 2.1 gigahertz band. However, if you look at the bandwidth, it's still the same, 100 megahertz. So this bandwidth basically so the bandwidth affect the data rate or the speed of the internet. So to overcome this limitation, where we can only utilize 100 megahertz bandwidth, that's why in 5G we use at higher frequency at the microwave frequency 3 to 300 gigahertz, where this bandwidth we can utilize it almost 1000 times from the previous 4G. That's why the speed will go up to 1 gigabit per second, higher than the previous speed. However, right now we're still in the progress for the 5G. That's why I stated here is still less than the 1 gigabit per second for the data rate. But however, in the future it will go higher than that. Okay, so if you look at this frequency, the evolution from 1G to 5G, the frequency is going higher because we can utilize higher bandwidth, and which affect the data rate, where we can produce higher speed data rate. So let's look at the different or the relationship between throughput, bandwidth and also data rate. So throughput is the amount of data that can be sent and received within a specific time rate. So however, bandwidth is a measure of how much data can be sent and received at a time. So if you look at this, the bandwidth, if you look at this picture, the bandwidth is basically is the pipe here. So the larger the pipe, can send more data at one time. So with that, we can, with larger bandwidth, we can have a higher throughput and also higher data rate. Okay. Okay, this is the explanation for the figures that from the slide before that I have explained. You can read it. Let's look at the frequency spectrum. So frequency spectrum basically start from 10 power 4 until 10 power of 20, where 10 power 4 we are using is the radio RF, and then it goes to microwave, millimeter wave, and then it goes to infrared and visible light, and after that goes to ultraviolet, X-ray and gamma ray. So for communication we use frequency from radio 10 power of 3 until 10 power of 4 frequency until around 10 power of 12 before the infrared or visible light frequency. So this is the spectrum, frequency spectrum for the communication. So we have a VLF, very low frequency, until EHF, extreme high frequency. So if you look at this is from 3 kilohertz to 3 gigahertz is the RF frequency, and then we have 3 gigahertz until 30 gigahertz is a microwave frequency, and then 30 gigahertz to until 300 gigahertz is the millimeter wave band frequency. So all of this band from 3 kilohertz to 300 gigahertz has their application, where at higher frequency EHF, extreme high frequency, used for radio astronomy, satellite communication, and at the lower frequency used for long range communication such as maritime radio and navigation. So at the middle here we use for most of the commercial application such as broadcasting, cellular, Wi-Fi, GPS. So this is the list of the assignment, microwave radio RF assignment that usually used for the communication or application. So at low frequency usually uses for military, for and then we have satellite link or satellite cross link at the higher frequency. So this is the band where we name it L band, S band, C band, X band, KU band, KE band. So I think you already heard this band during your during the course before. So if you look at this, I already mentioned that for the radio wave communication spectrum, it uses from 3 kilohertz until 300 gigahertz wavelength. So at this spectrum, we divided into few types or zone. So the first zone is permeable zone, where the frequency in this range are considered more valuable because they can penetrate dense objects such as building or concrete. So at this frequency from 3 kilohertz until 2 gigahertz, usually used for long range communication, uses for GPS, it uses for broadcasting, cellular phone, or for remote control toys at, for example, 400 megahertz, and also for AM, FM radio. So mostly for long range communication, because at this frequency, this range frequency, it can penetrate dense objects such as building, forests, okay. And then we have a semi-permeable zone where the frequency is basically difficult for signal to penetrate dense object. So basically, if you have a building, it will be at this frequency, it will be absorbed and it will create loss. So this frequency from 2 gigahertz until 5 gigahertz is usually used for short range communication. For example, at 2.4 gigahertz, a Wi-Fi communication. So for Wi-Fi, usually you use it inside a building or a home where the range might be less than 100 meter. So for permeable zone, usually you can go up to more than few kilometers for communication. But for semi-permeable, the range for communication is usually around 100 to 300 meters only. Okay. So at 2.4 gigahertz band, basically used by more than 300 consumer devices, include microwave oven, cordless phone, and wireless network for Wi-Fi and Bluetooth. So at this band here, 2.4 gigahertz, it is basically free, which we call it ISM band, industrial, scientific, and medical band. So this band here, 2.4 gigahertz, is free to use for all of the people or citizen. So that's why there's a lot of application devices using at this frequency. So other than that, for example, for permeable zone, basically the spectrum or the frequency here is managed by MCMC, Malaysian Communication and Multimedia Commissioner. So this agency regulate the spectrum, and also if you want to use, for example, telco company want to use a frequency for their for cell phone, for example, Celcom or Maxis, they have to pay to the MCMC to use the spectrum or the frequency. So basically, the frequency is auctioned or sell by the MCMC. So that's why they stated here over here. So for the citizen, we can only use at 2.4 gigahertz because it is free. Okay. So other than that, in semi-permeable zone is where the radar, satellite radio, and also cable TV radio for satellite. Okay. We also have a UWB communication, ultra wideband communication at this zone also. Okay. And then we have a line of sight zone, where signal in this zone can travel long distance but could be blocked by trees and other objects. Okay. So in this line of sight, it can travel far away, few kilometers, similar like permeable zone. However, it should be in line of sight, where this communication cannot be blocked by any obstacle, any object. So usually at this band from 5 GHz to 50 GHz, it uses for Wi-Fi network. So we have another Wi-Fi network at 5.8 GHz around this part. Another is highway toll gate, police radar, and then we have a satellite communication at around 10 to 12 GHz at K and KU band, and we have a security alarm at this band also. Okay. And then higher than that is basically a short range communication from 50 to 300 gigahertz, mostly used for military or federal agent or specific industry. So this signal in this zone can only be sent short, unobstructed distance. So if you go to the MCMC, website, you can look at the Malaysia Spectrum plan, where they allocate the spectrum to industries and government application or usage. So from here, you know what band is for mobile communication, and what band is for use for satellite communication. Okay. And the regulatory body that I have mentioned before is MCMC, which stand for Malaysian Communication and Multimedia Commission. So Suruhanjaya Komunikasi and Multimedia Malaysia. So this the headquarters is in Cyberjaya. So for MCMC is our national regulatory body. In international regulatory body, we have ITU, International Telecommunication Union. So we have ITU-R and ITU-T. So R is the radio communication sector, while T is the telecommunication standardization sector. So the unit of power measurement that is commonly used in our course or in communication, RF and microwave communication, is dB, which is decibel. So dB or decibel is the basic yardstick used for making power measurement in communication. So for antenna, oscillator, filter, RF and microwave devices uses this unit for power measurement. So you need to remember this equation. So dB watt is equal to 10 log power in watts, or in dBm you can add 30 from this value here. Okay, so it's simple. So this is the wave propagation. It's basically composed or consists of electric and magnetic field for wave propagation. So if you look at this, the red color here, propagate, is the electric field, while the blue colors, wave, is the magnetic field. So with these two composition, it produces a wave propagation. Okay. So so if you look at this is E for electric field, B is the magnetic field, and we have Z is the wave number or the propagation vector. So to identify the lambda, so the lambda is one cycle of the wave. So from this point to this point is the lambda. Okay. So how we can calculate the lambda is using the C equal to F lambda. So if you know the frequency, you can get the lambda of the wavelength of the spectrum or the frequency. Okay. So this is the horizontal wave polarization for the magnetic field, and this is the vertical wave polarization for the electric field. And we also have a circular wave polarization, where this is a combination of electric and magnetic field with different phase. So with different phase, it produces a circular wave polarization. So what is EIRP, effective isotropic radiated power? So for EIRP, usually it uses to measure the power or power transmitted from a device, a communication device, and it uses basically in ITUR or in MCMC we have a standard where communication devices cannot be more than few hundred milliwatts of EIRP. So what is EIRP? EIRP is basically a signal strength times the effective area. So this is theoretical. However, for the calculation, we can use ERP is equal to the power transmit from a transmitter plus the gain of the antenna. So this is the equation that you usually use to calculate the ERP. For example, you have a access point, a router that transmit the power 100 milliwatts, and you are using an antenna of 5 dB. So you need to plus these two power, transmit power and antenna gain, to get the value of EIRP. Okay, we will look into it in the chapter, in propagation chapter, more the detail of it. Okay, and then we have a phase equation that you also need to know. I think this phase equation everyone knows. You already learned it in electronic communication system and other subject related with communication. So it is to to calculate or to determine the power received. For example, this is the transmitter and this is the receiver. So we want to calculate the power received at the receiver. So we use this equation. So we need to know the power transmit, we need to know the gain of the antenna at the transmitter and the receiver, and also the distance between these two, transmitter and receiver. So this phase equation, we're going to look into it more in the propagation chapter. So this is the equation for the phase the what we call abbreviation for the phase equation. This is for the free space propagation model, where we need to find the propagation loss. So to identify the propagation loss, you need to know the frequency, the distance, and use this what we call equation to calculate the propagation loss. So the propagation loss or the path loss, we can summarize it with this equation lah, where the path loss or propagation loss is equal to 32.45 plus 20 log f. The f is the frequency, plus 20 log d. D is the distance. So the frequency here is in megahertz and the d here in kilometers. So in this slide here, we also calculate the cable loss, because in cellular communication we use cable from transmitter to receiver where it creates losses. So we also need to include the cable losses in the calculation to calculate the power received. So if you look at this example, if a transmitter produces 50 watt of power, express the transmit power in dB. So dBm and dBw. So you can use the calculation 10 log 10 log power in watts. So you can calculate this first using this equation. So 10 log 50 watt, so you get 17 dB watt, and then to get the dBm you can just plus 30. So 17 plus 30 you get 47 dBm. Okay, and then B, if 50 watt is applied to a unity gain with 900 MHz carrier frequency, find the receiver power in dB at free space distance of 100 meters from the antenna. So in this equation they give power transmit, unity gain, 0 dB, 900 MHz frequency, and a distance of 100 meters. Okay, so we use the equation 32.45 plus 20 log D plus 20 log F. So insert the value in that you get. Kilometer is 0.1 kilometer, megahertz is 900 megahertz. So you just insert the value and you get the free space loss at 71.5 dB. So this equation is the free space loss or path loss or propagation loss. So from here you can use the equation to get the power received. So the power received, PT plus GT plus GR minus the FSL or PL lah, sama FSL PL is the same. So you get the value of the propagation, the power received. So it's simple, you just use the equation. And then what is if PR at 10 km distance? Assume unity gain for the receiver antenna. So you just change the value of this kilometer here to 10 kilometers, and from there you can get the value of the power received. So if you look at this, the value of 10 km, the power received at 10 kilometers is much lower than the 100 meters distance. So it shows that the longer the distance of two towers of the transmitter and receiver, the higher the free space loss or the path loss. Okay. So what happens if these two towers is not the same height? So the transmitter has a height of 50 meters, while the power received the receiver tower is 2 meters. So how to calculate it? So for this, you need to calculate the distance of these two towers using trigonometry theorem lah. So 48 is the length of the tower, 50 minus 2 meters, so you get 48 meters, and then the distance here is 10 meter. So 10 meters, so you get D here. So D here is basically 49 meters. So you need to use this value D or R here to insert in the free space loss or path loss. Okay. So you cannot use the 10 meter distance here because of the angle, because the height of the transmitter is much larger than the height of the receiver. So you need to use the trigonometry theorem lah, to get the actual distance from the antenna here on top of the transmitter tower to the antenna at the receiver. Okay, and then the process is the same. You use the PR equal to PT plus GT plus GR minus FSL. Okay. So this is also the basic thing that you need to know, which is the C over N, or carrier to noise ratio. C is the minimum received power, while N is the input noise power. So that's why it is important to get the carrier to noise ratio, because if the power is the receive power is below the noise power, so we cannot get any signal, we cannot retrieve any data from it. That's why we need to have a minimum receive power which is higher than the noise power. So to know this, the equation is C equal to C over N so to get the N value here, we use N equal to KTB. So C, usually we can use the PR equation, power received. However, N for the noise ratio, we need to use this equation here, N equal to KTB. So K is the Boltzmann constant. So you can use the calculator, press constant and 25, it is the value for the Boltzmann constant. T is the equivalent noise temperature at the receiver in Kelvin, so you need to know the Kelvin, and B is the bandwidth, noise bandwidth in Hertz. So in telecommunication, the carrier to noise ratio often written as CNR or C over N. So these two abbreviation or term is the same, CNR or C over N. Okay. So you shouldn't confuse about on CNR or SNR, so carrier to noise ratio, and also signal to noise ratio. So the signal to noise ratio, SNR, is a modulated signal, while CNR is an analog baseband signal after demodulation. Okay. So higher C over N or CNR or SNR ratio provide good quality of reception. Okay, so how much CNR or SNR required? So let's look into it. So if you look at this, higher than 40 dB SNR is, we call it excellent signal, 5 bar for for cellular communication, and 25 dB to 40 dB SNR equal to very good signal, 3 to 4 bar. And if you look at this, 10 dB to 15 dB SNR, we usually put it as a very low signal, 1 bar. So if you look at your handphone, if it's 1 bar, means the signal to noise ratio is really low, around 10 dB to 15 dB. Okay, so you need to usually move to a different location to get a higher signal, so that the signal power is much higher than the noise noise level. Okay, and usually at no signal or no go is less than 10 dB SNR. So this is an example of the origin, true signal, and noise. Usually noise is at the lower part here. So you need to make sure that the signal or the origin, the signal is much higher than the noise level here. Then we can get the signal. Okay, so the higher the gap between the signal and the noise level here, the good the quality, the what we call it, provide a better or good quality of reception. Okay, hope you understand about it. So let's look at the example for the CNR. So to find the calculate noise power for T equal to 290 Kelvin and 1 Hertz bandwidth at room temperature. So N equal to KTB. So K is the Boltzmann constant, T is the temperature in Kelvin, and 1 is the bandwidth in Hertz. Okay, so in dB you need to put 10 log lah, or else you get different value. So use this 10 log to get in dB, and if you want to change it in dBm, you just plus 30. Okay, and let's look at the example number 2. Sorry, number 5. A wireless link is constituted by 2 antennas operating at 2.4 GHz and distant 5 km. Minimum carrier to noise ratio is 25 dB. The transmit antenna is 15 dB, receiving antenna is 10 dB, and then the transmit antenna are placed at tower height of 500 meters and the receiving antenna height at 50 meters. So what should be the transmit power in watt in order to achieve the minimum CNR or C over N? So it also gave the noise the temperature, noise temperature, and also the bandwidth. Okay, so if the equation is in a written form or in text form, it's better for you to draw the actual scenario. So if you draw it like this, it will be much easier to understand. Okay, so we have a distance and we have a height, different height, and the gain of the antenna, transmit and receive antenna. We also give the temperature and bandwidth. So Right now we don't know the transmit power here, and also we know the operating frequency is 2.4 gigahertz. Okay, so the first thing to do is to find the distance between this antenna to this antenna. So use the trigonometry theorem to get the D over here. Okay, so D is 5.202 kilometers. So from here, you know the distance between the two antenna, transmit and receive antenna, you can get the FSL, free space loss or path loss, which is at 114.07 dB. Okay, and at the same time, you can also calculate the noise, the N, which is the equal to KTB. So 10 log K times the temperature times the bandwidth, you get the value over here, the N value, the noise value. And after that, to get the C, because we don't know the power transmit, so and they give the C over N or CNR is 25 dB. You can use it to get the C, where C basically is the PR. So PR. Okay. So basically the question is we want to find the PT. So not PR. So we need to find the PT over here. So that's why we utilize the C over N, which is this value is we get it at the receiving part, at the receiver. So C basically here is the power received. Okay, so use this. So you need to remember that if it's in dB, so C over N, the division here will become minus. Okay, C minus N. So in dB there's no multiple or division, there only plus and minus. So if there's a division, you need to change it to to minus lah. If it's time multiple, you need to change it to the plus. Okay. So in this part, you know that the C over N is 25 dB and N is minus 120.15 dB. So if from this equation, we know that C is minus 95.15 dB, which is the value of the power received. So from here, we can use the PT equal to the first equation. PT for this equation, we need to change it where PR is over here and PT is inside and on the right side. So PR is equal to PT plus GT plus GR minus FSL, and you get the PT value. So to change this dB into what, you just use the anti-log, okay, to the value. So for this example 6, you can try to do it by yourself. So in this question, you give the C over N equal to 10 dB, noise temperature 290 Kelvin, bandwidth 100 MHz, and frequency at 2 GHz. So you need to calculate the required distance between the transmitter and receiver. So you need to know the distance between this transmitter and this receiver. And you also give the GT or gain, antenna gain at the transmitter 10 dB, and antenna gain at the receiver is unity gain, which is 0 dB, and the power transmit is equal to 10 milliwatt. So the same solution that I've showed before in example 5. So you need basically you need to find the PR first. From the CN here, you need to know the PR, and you use the first equation to get the FSL or PL, the path loss or the free space loss. Try to get it, the value of the FSL, and from there you can get the distance of the transmitter. Because once you know the FSL, you also know the frequency, so you will know the distance of the two tower here, transmitter and receiver. Okay. So another fundamental thing that you need to know for the wireless communication is interference. Okay, so there are multiple type of interference, such as multipath fading, so interference and multipath fadings. So from here, for this picture, we have multiple devices using the same frequency or spectrum for communication. So for example, here we have two phones which are used for cellular, so it has the same spectrum. We might produce interference between these two. Okay. So in communication and electronic, especially in telecommunication, interference is anything which modify or disrupt a signal as it travels along a channel between a source and receiver. So the term typically refers to additional of unwanted signal to a useful signal. So typical value used in practice is usually carrier over interference should be larger than 13 to 18 dB for analog and larger than 11 to 15 dB for digital system. I already mentioned it to you about the ISM band, Industrial, Scientific and Medical band, which is basically free to be used by citizen and also industry. So you don't have to require license from the MCMC to operate at this band. So in this band, basically most of the industry use at this 2.4 gigahertz band, 2.4 until 2.4835 gigahertz band. For the Wi-Fi, we also have 5.7 to 5 to 5.85 band gigahertz here for point-to-point communication. This is also free, and we also have a 909 to 8 megahertz band here. And at the low frequency here, we have another band which is at 433 megahertz, which is also free to use. More for the application, usually used for IoT or for long range communication. Okay, such as we call it IoT application, LoRa communication. So for IoT at 2.4, usually we use Wi-Fi or Zigbee. Okay. So I think that's all for the introduction. You already know most of the part that you need to, the basic part that you need to know on propagation, on interference, on the RF and microwave, and also on the spectrum, right? So after this, we're going to go on details or more on the antenna, microwave and RF devices, and also on the propagation. Okay, so that's all from me. Thank you. Assalamualaikum.